Heat transfer by conduction, that is conduction of heat through metals in a steady state. We'll discuss about conduction of heat in a metal in a steady state. Here the heat can flow only when there is a temperature gradient, that is there is a temperature difference, that is heat flow from the hotter surface to the cooler surface or hot surface to the cold surface. Whenever there is temperature gradient, there the heat transfer can occur. This is given by the equation, that is heat transfer rate is equals to driving force by resistance. Okay, now driving force is also known as temperature difference, that is delta T, and it is again given is the temperature difference, that is heat difference. Okay, resistance term is represented by the Fourier law. Fourier law has given the equation as resistance is equals to thickness of the surface by mean proportionality constant into area of surface. Okay, so this is equation can be written in a symbolic form. When we write this in a symbolic form, you get the equation as resistance is equals to L by Km into A. So equation 1 was driving rate is equals to driving force by resistance, and equation 2 is resistance is equals to L by Kma. Now we have to prove these 2 points, that is delta T by resistance, and second is resistance is equals to L by Kma. These 2 equations we have to prove, and the Fourier law has for conduction is discussed now. The Fourier law has stated that rate of heat flow through a uniform material is proportional to area and temperature and inversely proportional to length of path flow. Means whatever the rate of heat flow is there, it is directly proportional to area of the surface in which the heating is going on and temperature, and inversely proportional to the length of the path flow. This is given by the equation area into temperature difference by thickness. Okay, again when we convert this into a symbolic form, we get the equation as Q into, that is Q is a heat transfer, heat flow is directly proportional to area into temperature difference and divided by thickness, it is inversely proportional to thickness. Okay, thickness here is given as L, A is the area, and delta T is the temperature difference. Okay, when we remove this proportionality constant proportionality symbol, and when we introduce the proportionality constant, the equation becomes Q is equals to Km A delta T by L, delta T by L. Okay, this is equation number 3. Let us take one metal wall, let us see one metal sheet is there, a metal wall is there, and it is having 2 surfaces, that is one surface here and second surface is this one, that is the low temperature side is this one, this is the high temperature side. Okay, and this high temperature side is the H side and low temperature side is the C side. Okay, now this metal sheet at the center, the intermediate part, this middle part is given as DL. This is the complete area of the metal wall, and L is the thickness you can see. Okay, so there is 2 points here, that is low temperature side and the high temperature side. We will see the derivations now. A is the area of the wall, metal wall, L is the thickness of the metal wall, H is the side of the wall at the high temperature side, C is the side at the low temperature side, and DL is the intermediate part, that is in between part. The heat flow will be in a steady state. Okay, so in this section, in this DL is the intermediate part, it is parallel to both H side and it is parallel to both C side. Okay, so let us see the application of this Fourier law in this DL section, in this middle section, how we apply the Fourier law and what will be the heat transfer, and whether the equation 1 and 2 are being proved or not, we will see in this topic. Okay, so when we apply for DL section, when Fourier law is applied, the equation becomes dq by d eta is equals to minus ka dt by dl. Okay, dq is a heat transfer and eta is the time, and k is a proportionality constant, t is a temperature constant. Temperature constant. This is equation number 4, and the minus sign present over here, it indicates decrease in temperature, drop in temperature in the direction of flow, as it is 2 sides are present, it is high temperature side and low temperature side. So minus side and the sign indicates a decrease in temperature whenever the heat flow is going on. This dt by dl represents the temperature gradient, that is difference in temperature. Okay, so for steady state, whenever we talk about steady state, heat transfer will be in a equal form. So equation 4 will be changing to the when we change the equation 4 to the constant heat transfer equation, we get the equation as q is equals to, that is dq by d eta is changed to q is equals to ka dt by dl. In place of q and d eta we are writing as q we are writing, why we are writing, because it is discussed in a steady state. The metal wall is in a steady state form, so we are introducing q here. Q is equals to minus ka dt by dl. It is equation number 5. The temperature drop in the DL section is not known. It is between two sections. One side is hotter one and one side is the higher temperature, another side is the lower temperature. In between DL is there. But in DL portion the temperature drop is not observed. So the area may vary, the area of the metal wall may vary with the length of the metal wall, but it is independent of temperature. Okay, the area of the metal wall will be different from the length of the metal wall, but it is independent of temperature. And by separating the equations of this minus ka dt by dl, when we separate this equation, that is minus k dt is equals to, and we are sending some terms over there, we get the equation as minus k dt is equals to q dl by a. Okay, so we get the equation 6 as minus k dt is equals to q into delta dl by a. This is equation number 6. When we integrate the equation number 6, okay, when we integrate the equation number 6, we get the equation as q is equals to integration dl by a, okay, is equals to integration minus t2 t1 k dt minus t2 t1 k dt. Okay, so we get the integration equation as dl by a at the limit 0 and in the limit t2 and t1 minus t2 and t1 k dt. As there is a heat transfer going on, drop in temperature going on, so minus can be removed here, removing this minus sign, and we get the equation as, we are just substituting, in place of t2 we are writing as t1 and t1 place we are writing as t2. So we get the same equation, that is q is equals to under limit 0 dl by a is equals to under limit t1 t2 k dt. Okay, when we again simplify this equation, we get the equation as q into L minus 0, that is limit 0 by a is equals to km T1 minus T2. As we are talking about temperature difference, that is T1 and T2 is there, so T1 T2 km. Again, after simplifying this equation, we get the equation as QL by A is equals to km T1 minus T2, and in place of T1 minus T2 we can write as delta T, hence km delta T. So QL by A is equals to km delta T. When we rearrange this equation, we get the equation as Q is equals to km delta T by L. Okay, so when we rearrange this equation, that is QL by A and is equals to km delta T, we get the equation as Q is equals to km A delta T by L. Okay, so here km is a mean proportionality constant, and in steady state heat transfer remains constant, that is Q remain constant, and the term delta T represents driving force or temperature difference. So again, by rearranging this, we get the equation like Q is equals to delta T by L, and again we get the equation as by km into A. That is, two equations are proved. First the equation 3 is proved. Now when we again change this equation, we get two equations in it, that is Q is equals to delta T by L, and again after rearranging we get the equation 2 as Q is equals to L by km into A. Okay, hence we have proved all the three equations, equation 1, 2 and 3. This is about Fourier's law of conduction.